like, please interrupt me with questions. Thank you first. Thank you really a lot for introduction, for invitation. It's really great to be here. I am still very new in Israel. It's my first opportunity to speak in Bar Ilan, but I really hope not the last one. And please feel to interrupt me with questions as much as you wish. I have just 15 slides until some summary. So I don't have to show you a lot. So it's absolutely, I'm very much used to be interrupted. Today I will talk about subradiant states in waveguide quantum electrodynamics. And basically only system I will describe, like only model I will talk about will be this photonic waveguide. So this tube is a waveguide, photons can propagate inside it. And then this waveguide is coupled to two-level atoms. And I will talk what I mean by two-level atoms, like a series and what exists in real life. But just let me say for now, there are two-level atoms. Now they can be in the ground state or they can be in the excited state. And if they are in excited state, they can spontaneously emit photons only in the waveguide in the model which I consider. So, but then you can get constructive or destructive interference, and I will talk about destructive interference of photon emission from atoms coupled to the waveguide. So it's the whole subject of my talk, but first I will try to make a more general introduction into all these atoms, waveguide, photons, why this is interesting, why we are studying it. Okay, it's on this computer. So we are studying atom-photon interactions in a waveguide, and what is so special? Okay, let's first go to atom in free space. So what do we know about it? So if we have excitement, it will emit photon after some time, but there are kind of two problems. First, you don't have much control about the spontaneous emission. Photon can be emitted everywhere, and also interaction of free space photon with an atom is not so strong, just because basically atom is small and photon is wave which propagates everywhere. So interaction with a plane wave with a small atom is usually not so strong. So what you can do? Typical way would be to confine all photons in a cavity, and then they are all confined, and then photons are emitted into single mode, and interaction is much stronger because electric field in the cavity is stronger, and it's all in a single mode, and this is cavity QED, and it's a fascinating topic. So Ella is doing it, and I'm sure many other people here are doing it, and I will not talk about cavity QED today. I will talk about just slightly more different setup. I will talk about waveguide QED. So my photons, instead of being confined in all three directions, will be still allowed to propagate here or there. In two directions, they are confined. So my electric field is still a bit enhanced in the waveguide. My interaction is stronger, but what's more important is that it's directional. So now it's a one-dimensional problem. Atoms emit photon only there or there. And contrary to cavity QED, you now can study transport problems. So if I have an array of atoms which are coupled to the waveguide, a photon can be emitted here. It can propagate some distance inside the waveguide, then it can be reabsorbed by another atom, then it can be probably re-emitted back, again reabsorbed. So in this system, you can study not just spontaneous emission and absorption, but you can study propagation. So this is a problem with some transport, some movement, degree of freedom. And this is what makes it different. Yeah.
So if you had the waveguide was full of, for example, diamond electrodes, you would consider them some sort of like continuum approximation for permittivity. in this case, you're obviously considering the limit of few atoms, like, but how few is too few and or how many is too many?
So, excellent question. So I guess ideal system for me would be like 10 perfectly periodically spaced superconducting qubits. Better 100, but if I say like 100 perfectly spaced superconducting qubits, experimenters, well, everyone in the audience would be a bit surprised. But also what people do, people can say have a cloud with 1,000 or 10,000 atoms, which float around the waveguide. This is interesting enough for me. People can also, maybe I'll skip back and skip forward and then I will return. So ideal system is something like that. So you have a microwave photons, which propagate inside a microwave transmission line. Your spectral range is 10 gigahertz. And then you couple these transmon qubits, which act as a two-level atom. It's a bit a story why you can consider actual transmon qubit is not quite a two-level atom, but still it's a good approximation. Now you can also have cold atoms which are trapped near a nanofiber. So this operates in optical spectral range, say rubidium or cesium. You can also have cloud of Rydberg atoms, which is kind of same thing, but you can also have quantum dots, say single quantum dots, which is positioned in a nanophotonic waveguide. You can have, instead of a quantum dot, you can have defects. I think here there are silicon carbide vacancies, and they are also near a waveguide. So these are solid state systems. Now this picture is borrowed from Ronen Rappaport, also not so far from here in the Hebrew University. So what they do, they try to use excitons, electron hole excitations in a semiconductor as an analog of atom. And the only problem is that this system so far operates not really in a quantum regime, they have more than one photon. So typically experiments that they run operate in regime with say 10 to 100 photons. And what you ultimately want to do, you want to push the system to the regime where quantum nonlinearity is manifested even for 1 or 2 photons. So why do you have quantum nonlinearity? Because one two-level atom cannot absorb 2 photons at the same time. So you have photon blockade. So what people try to do with this system, they try to go in this regime of extreme quantum nonlinearity, photon blockades, when just propagation of first photon affects the second one. So, and people try to say, okay, this maybe can be a quantum gate, or maybe this will be a connection between blocks in your quantum computer. I'm not into quantum computing myself. I'm more into, say, quantum simulations. So what I am interested in, yeah.
Question.
Yeah.
How does the quantum defects can we know that waveguide propagations?
Sorry, could you say it again?
How does the quantum defects can introduce that waveguide?
Quantum.
How can this quantum defect be introduced?
Okay, so they do some but like some ion etching, I think. So the way, so I really not an expert, but you have your nanophotonic waveguide. So then you take your ion beam, it creates a lot of defects. Now the ideally, like at very point where you have a beam, you have a defect. Now I guess the art is to have just one defect per beam and to have them in a controllable way and all identical. So actual problem is in homogeneous broadening, both for quantum dots, for quantum defects. So they all turn out to be a bit different. And then they cannot coherently exchange photons between each other. And in actual experiments, if these are quantum dots, okay, you can have two identical, maybe three. The same with quantum defects, two, maybe three. But if you want to study some transport phenomena, you better have at least 10. So this you can have with superconducting qubits, but at least at the moment, not with defects, as far as I know. Yeah.
On the same opportunity, are you also assuming that they are that you don't have direct coupling between them, so not through the photon field, but like coupling, tunneling, for example?
Yeah, there is no direct coupling, only via the photons. Now, for superconducting qubits, it's a perfect approximation. For quantum dots, it's also a perfect approximation. If you say have free space atoms like that,
Yes.
then only 10% at best of emission goes through the waveguide, and 90% emission goes to free space. So they talk to each other 10 times more through free space than through the waveguide. You still can have some effects, but it's a challenge. But for superconducting qubits, 99.9 and 1 more 9% of coupling goes through the waveguide, the base setups. Now, like, what is so special about it? So I'm not going to build a quantum computer, I'm going to study some physics. So, okay, one-dimensional system, what's so interesting in this physics? I want to compare, let's say, with Bose-Hubbard model. So you have some anharmonic tracks, and then you have your nearest neighbor tunneling. So this is your typical Hamiltonian, say, solid state or quantum. Many people are very much used to. So here you can think of the same anharmonic traps. Your two-level atom is an extreme case, very anharmonic trap. So this can be the same. And they interact to photons, to continuum of photons. And you have your dipole coupling, again, rotating waves. So this is your photons propagating the waveguide coupled to atom. And it's a super hard problem because you have a continuum of photonic modes. So there are ways to deal with this directly. But in principle, your Hilbert space is huge as soon as you have more than one photon, and it's not really tractable even in this setup. So what people usually do, what is a good approximation for actual systems, is to trace out photons. So you just say that speed of light is very, very fast. And then you can assume that photons instantaneously propagate between the atoms, and they just mediate the interaction. So then instead of this, like correct Hamiltonian, you can, in some approximation, replace this by your effective Hamiltonian, where photons are excluded. And the only thing which remains is this long range coupling between distant atoms. So like photon is emitted here and reabsorbed here. And it's even not just a long range, it's infinite range coupling, because in my ideal model, photon can propagate very, very far along the waveguide. So it's a model with long range coupling. And what is kind of worse is that this Hamiltonian is non-Hermitian, which is in principle a bad thing. You should better use your master equation, and it's a no. But why it's non-Hermitian? Because it's an open system, so your photons can escape into the waveguide. So it's spontaneous emission. You have loss of photons. So if you have just one atom, this Hamiltonian reduces to minus I gamma 1D, where gamma 1D is just your spontaneous decay rate. So yeah.
You assume that the incident photon and the emitted photons are degenerate, same frequency.
For now, there are no even incident photons. So
you have to have some excitation.
I
Some
will.
of the atoms have to be excited. So there has to be some excitation someplace.
Yeah, in real life for sure, I will consider eigenstates. So what I will do during this talk, I will just consider eigenstates of this thing. In reality, like in actual simulation, if you want to describe particular experiment, you have to introduce, say, coherent driving, and you have to solve a problem with a Hermitian part of this and dissipation because of the photon emission. And then your coherent driving, it can be in resonance with atom, but it can also be off resonance.
But just in a simplistic model, in my mind, if I had a channel, photonic channel like this, and I excited some of the atoms, a single photon excitation went in, all I would do is cause a delay. I would get an emitted photon sometime either in this direction or in this direction with a certain delay. And that delay would be just dependent on how many absorptions and re-emissions I had, right? So the stronger the absorption, the re-emission, the further there's no losses. Photons never disappear.
Yeah, I agree.
So it would just be a delay.
Yes,
in the amount-
yes,
The
yes,
time it takes for the photon to
Yes.
come out, one or the other with the check.
yes. So what happens? So short answer is yes. And it's even inside this reduced model. So if you take a very large system, what are the eigenstates of this system? They're like coupled atom photon modes, which are polaritons, which have other dispersion. So let me maybe even may
Yeah.
so I am now talking in, say, classical optics or single photon level. So this is my atom resonance, and then this is my photon dispersion, CK, and then I let them interact. So I get avoided crossing, and I get two polariton lines. And the delay, it's basically because, well, these things propagate slower than light. So all this reabsorption and re-emission, it translates into formation of polaritons. And then this is a single polariton picture. But now suppose I put two polaritons. Now those would interact because my atoms are anharmonic. So this whole thing I will going to talk in the remaining time is about interaction of two polaritons with this dispersion because of this quantum whatever Kerr nonlinearity.
So, sorry, Barbara, just, I'm trying to understand this, exactly this point of the long range interaction. Because you have long range interaction on the other hand, on one hand, and I can see it mathematically, you just trace out, that's fine. But then you have like two atoms, and between them, there's a million other atoms. I mean, they're not going to interact directly, the photons are going to be absorbed and be emitted many times before they reach from here to here.
Well, you have to take all of this into account. Maybe as a, let's assume they are all in one point. Somehow, all z are zero.
Okay.
Then it's kind of a decay model. So you have all-to-all interaction, which is just all with all interact at the same time. Now, only difference from the decay model is this phase delay term, because there is some spacing. But it turns out that because of this phase delay, you get new effects. So with this, the problem is solvable, and it was solved in various versions. It's integrable. You can solve scattering problem. It's just relatively easy. And this phase delay, this is what introduces some physics. So in fact, I have an open system with long range coupling, and this is not so typical.
The long range is just the open boundary.
Yes, yes. So I can also, like, if I were talking in a very condensed matter audience, I would say that, okay, I'm studying interaction with of this kind of particles with an extremely non-parabolic dispersion. polaritons have very non-parabolic dispersion. So this is non-typical. Like if you open, I don't know, your Latinger liquid, whatever, your favorite one-dimensional system with interactions, usually single particle spectrum will be easier. So it's an open problem, how particles with this kind of dispersion interact in a quantum regime in 1D, also in the presence of loss. And this is why we are working on it. So here we've been, so like we covered this, we covered this. So we are going to study the states where spontaneous emission time will be long. Only for these states I can actually use effective Hamiltonian non-Hermitian because they will have very long lifetime. There will be almost no quantum jumps. And my question is like, if I excite this system, I measure some correlations. What is the longest lifetime of the correlations I could get from this system?
What correlation? Correlation of what?
You can think of some, well, let me use my raising operators, like B, like this. Suppose I have excited my system. I have access either to just photon emission rate, or if I can measure locally to this. So how this will depend on time after my excitation pulse, and how this will depend on J and J prime. So it's like sort of where we are.
So J primes. Sure.
No, but I excite my system, so I give it an excitation, and then there will be some dynamics, and then this dynamics will have some lifetime. So after there will be no excitations after some time, and at long time this will evolve into something. So into what will survive, which kind of correlations will survive. So what will survive will be determined by eigenstates of the Hamiltonian I've just shown you. And I will, well, depends on timing, I will show you the case of weakly excited subradiant states. Maybe I'll talk about stronger excited subradiant states. So, sorry. Okay, so maybe, so what are subradiant states? They are states where spontaneous emission from different atoms interferes destructively. And you can understand this even when you talk about classical antennas. If you have all your antenna emitters in phase, there is constructive interference and your spontaneous emission intensity will be more, but also your emission lifetime will be shorter. So this is all like a very naive classical picture of, say, decay superradiance. Now, if you have destructive interference, some of atoms point up, some of them point down, you have suppression of spontaneous emission. Why it's important and interesting for me? Because there are many ways to realize a subradiant state. So I can flip some of the atoms like that, and this is all subradiant. There are many ways to get the sum equal to 0. So your space of subradiant states is highly degenerate. I sometimes give this Tolstoy thing, you know, all happy families are alike, but each unhappy family is different from each other. So all superradiant mode, everything is in phase. But all subradiant modes are different from each other. The space of subradiant modes is highly degenerate. And we know from other examples in physics that this degeneracy is going to be lifted by interactions. Effect of interactions, of harmonicity, of some other effects will be very important. So we are going to study how this degeneracy will break down and what will it lead to. So, and I will start with simplest case where you have either only one excitation in the system, or here is a sum over m and n somewhere, I'm sorry, or you have just two excitations in the system. So one excitation in the system, we even kind of discussed this polaritonic. Yeah.
ask, so this disruptive interference case, it will influence the long range interactions of the Hamiltonian that you showed previously?
It's inside there, kind of. I would say like that. So if you have destructive interference, you have longer lifetime and you give particles more time to interact. So interactions will be manifested stronger for states with long lifetime and with destructive interference. If, like I will write in the grant proposal, of course, I would say that subradiant states allow you to store the excitations and to process them. And this is actually truth. So I am studying single excited and double excited states for now. And okay, so what are subradiant states? Let's think physically. So subradiant states are states with suppressed spontaneous emission. I can explain this on a very classical optics. They don't have good phase matching with photons. My only spontaneous emission is emission of photon along the waveguide. So we already have this picture. It's even much easier to explain on this slide. So this is my photon line, and this is my key, and it's a periodic array, so it's pi over d. And I am considering in this talk only arrays with d much smaller than wavelengths. So this is the same as lambda over 2 pi. So it's closely spaced atoms. So this thing is much smaller than h of Brillouin zone. So if my excitations are mismatched with light, they will not emit much light. You don't have. So if this is my line of K, here somewhere is the K of light. This is pi over period. So these guys, they would emit photons strong. And this no, because there is a huge momentum mismatch. So in a large system, I would expect that only these emit light. In infinite systems, again, your question, I have spontaneous lifetime is infinity, because there it's like this theorem, Ewald-Tozen one. So you, like, if you are in a waveguide, you have nowhere to get out. There is this like Russian saying that you can sit in prison, you can walk in prison, but well, you are captured inside this thing. So, and maybe I'll skip this, it's another way to think of that. So you have all your dipoles on same atoms. If they're in phase, this is subradiant, and if they're out of phase, if relative phase is pi, then this is subradiant. You have a huge momentum mismatch. Yeah.
So just a second ago, you were telling us that all of the subradiant states, all of them are different. But can
Yeah.
you open them in the basis of just plane waves?
Yes, for single excited plane waves is a good basis.
Okay, for the single one.
For single one, so for single one, because you don't have interactions. So
Okay.
this is almost in infinite system, this is an eigenstate. In finite system, eigenstate will be a standing wave and not a running wave. That's it. So single excited case we already considered. Now let's move to double excited case, which is, let's put two spin waves, something like that, and let them interact. So why they will interact? Because atoms are anharmonic. So you cannot have two excitations on the same atom, like the sigma m squared is 0. So they will interact. Now, how they will interact and how will the correlations look like? So I could think of two spin waves with two momenta. Again, I could try this picture depending on k. So here I have only one k, here I have two k. Then, based on what I told you before, these things are very well matched with light. So this is just false color, it's not a calculation. Just when both k's are small, I expect strong spontaneous emission. My both photons are phase matched with light. And here I show like what I can do. I can diagonalize the Hamiltonian, which I have shown you, and plot an eigenstate, and the brightest eigenstate with the largest imaginary part will look in space something like that. This is psi mn squared. This is square value. This is joint probability to have excitation one on this atom and one like on that atom. So it's a two-particle correlation function. So, and it's pretty homogeneous in space. And this is the same, so as this is the decay state. Everything is homogeneous in space, nothing interesting. Now, this level of, and like this is your decay state, phase matched with light, everything else is dark. This was level of understanding in this field before 2019. I guess no one was just interested. And then they started to make these structures in reality and to look what you can measure and what you can calculate. So what people realized 5 years ago was the spatial structure of the darkest state, most subradiant states. So what are most subradiant states? These are states where both cases are close to pi over period. Like your both photons are mismatched with light. So this is of course the darkest state. Now, how does this correlation look like? It looks like two plane waves, but at the diagonal, so diagonal corresponds to two particles being in the same place. And there is not much here. They try to stay away from each other. So this is a combination of two plane waves in an antisymmetric way. And what actually happens, this is a model which can be mapped to the model of interacting hardcore bosons in 1D. And it is known that since 70s that these hardcore bosons exhibit fermionization. They stand apart from each other, like your bosonic excitations, which strongly repel each other, start to behave like fermions, and fermions try to be away from each other. And this is exactly what happens. They try to minimize wave function here. So this is most subradiant state in 1D in this model, and this is what was known, I guess, before we joined the field. So what you can do next? You can look at so this corresponds to 2k being close to pi, this corresponds to 2k being close to 0. And what else you can look? You can look at a general case somewhere in the middle. Like, yeah, question?
All this is business depend on the dimensions of the channel of the waveguide.
On dimension of what? Of system?
Yeah.
It only happens in 1D. So it's everything I talked today here is 1D. Fermionization is a 1D thing. You're in 2D, I think it's even not you cannot do like that. But so what we looked at a very general state. So what will be the result of interaction of two very general spin waves? And the result will be something like that, where this thing is no longer two plane waves. So what you will have something, don't know how well it's seen, but it's basically quantum chaos. So it's not regular in real space. It's also not regular in momentum space. It's a superposition of many plane waves of the order of the size of the system. So all these plane waves, they mix with each other and create chaotic correlations. So basically your model is not integrable, but that does not work. And why this happens? Because your dispersion is not parabolic. So your polarity and dispersion is non-parabolic, and this is a strong resource you say for new physics here. So people did not apparently, at least as long as we know so far, did not look much into interaction of particles with this kind of dispersion. Because it's non-parabolic, problem is not integrable. Like only here, near the edge of the Brillouin zone, you can approximate this by a parabola. Because, well, at the edge of the Brillouin zone, due to symmetry reasons, your curvature has to be 0. And then you can approximate it by a parabola. And for parabola, the model is solvable and gives you this. But as long as you are not at the edge, as soon as one of the particles has k not at the edge, okay, then you have something complicated.
But this is just, what you're showing there is just one of the modes, it's the ground.
It's your
state.
typical mode. No, it's not. It's a typical double excited subradiant state. It is a chaotic one. Unless, like, you have to look at all your spectrum. There will be different energies, but I want to talk about different lifetimes. So all these have very long lifetimes. This has the longest, but this also have pretty long lifetime. And your typical state with momentum, like you do a Fourier, and then you look at the typical absolute value of your k. So if it's somewhere here, then in real space you have something chaotic.
How do you change your position in this K space by changing the phase matching?
No, it's just you have a lot. Sorry, I've not been clear enough. So there are a lot of eigenstates. So what you do, you have your two-particle Hilbert space. You haven't Hamiltonian. You diagonalize it. You get n squared eigenstates. So there is some symmetry. So like n squared over 2. And then you start looking at all of them. You can do a Fourier and map your eigenstates to this map, but it's you don't select them. It's a eigenstate of the system.
So you get them all the time.
You get them, they're just there. Like a proper way, I guess the question is how can you excite them and how you can measure them, which is a hard question. So you have to excite, people have done something like that for small arrays. You can excite locally, put say 2 photons with a given phase between them, and then you can try to excite them, then you can try to measure what happens. But in principle, this is not a result of external excitation, it's just eigenstate of the system.
That would be external excitation, but it's dark.
Well, it's just a little bit bright.
Yes.
So yes, of course, it's if it's infinitely dark, you can neither, yeah.
Yeah.
But this is your natural eigenstate in the system, it's chaotic.
But on the ground states, right? On lower.
Ground states, I guess, even like all your atoms are in the ground state. So nothing,
Okay, yes.
because it's an open
Yes, yes,
system.
sorry,
So
yes.
at infinite time, unless you drive it,
Fair enough.
which we also did, but I'm happy to talk about it after the talk. It's just, so now what happens here? If you look at your typical, so like what we actually did, what the student did, we calculated n squared eigenstates, and then we started to look at all of them, and then it's easier to classify them by your typical value of the Fourier coefficient. So if one of the momentum is large and one is small, so like you have a polariton here and another one here or here, they will create states which tend to exhibit localization. And why it happens? So this is a state, this is a bound state, localized on an H, but even I would just say this bound state of two particles. So they travel with a small distance with respect to each other. So it's kind of an analog of a soliton in a very, very low particle region. Your two particles tend to stay close to each other, but then they can propagate with some center of mass coordinate. Now, this thing, I guess it's a new type of quantum correlation, which we found specifically in the system. And so far, I have not observed it being predicted anywhere else. So in a finite array, you can have a situation where one of the particles is localized at an H and another one forms a standing wave, or vice versa. So you have your two interacting particles in this system. And if they don't interact, they just form standing waves. It's not interesting. It's just standing wave of these polarities. If they start to interact, you can get these interesting correlations when one of the particles is on the edge and another one can propagate.
It's on the edge, can be the outside.
It can, but everything is out of phase. So with it has a lifetime, but it's just super long. in principle, eventually it will, but before it will, this correlation will develop. So two particles trap each other at the same time. Particle A traps particle B, but they are indistinguishable. So particle B traps particle A. Like for specialists, this is a interaction induced by Andre-Harper model. So you kind of have this, and the finding is, so why this localization happens at corners? So the reason is very simple, that here, so localization happens when one of the particles has very large momentum and one has small momentum. So the common thing between these two is that this particle is heavy, so it's easy to get localized. And the light particle is not so easy to get localized, so you still have some propagation. So here they, like here the mass, the center of mass, mass for the bound state is given by the mass of this particle. And here what happens, one of the particle literally traps another in the basis of the standing wave. So still have like 10 minutes, right? So good. So then I will skip talking about this thing. Kind of already discussed it, but what I will do, I want to talk a little bit more. So the lesson from the first part of the talk is that interesting effects hide at corners. Interesting effects hide at corners of your Hilbert space, where one of the particles has small momentum, another has large. So it is no sense to talk about bright states and dark states. It's the world is richer than that. If one particle is bright and one is dark, you can have interesting effects. By that I mean spatially localized correlations. We tried to use for some time term twilight states, but now somehow we are not using it. But really, there are a lot of degrees of freedom given for two excitations. Now, what we can expect if we have even more than two excitations. So I will show you just two slides on that. So let's start with two atoms. Very basic case. So you have two atoms and one excitation. So before going to multiple, let's remember the case of two. So I have my effective non-Hermitian Hamiltonian. I'm looking for its eigenstate. Imaginary part of energy gives you decay rate. I'm interested in case when this is small. Decay rate is small. Spontaneous emission is suppressed. Let's do this together for n equal to. Probably I should have done it like on slide 2, but now it's still the time. So I have two excitations, something here, something here. So I have two atoms and one excitation, which is either here or there. So I substitute this thing here. Phi is omega naught d over c, and I have 2 by 2 matrix equation. So this is minus I gamma 1d spontaneous decay of this atom, spontaneous decay of this atom, some delayed interaction. Sorry?
F.
F fill factor. This will be important. One excitation per two atoms means fill factor 1 over 2. This is very important. Yeah, thank you. So I diagonalize this, and my subradiant state is this dimer. Two excitations in opposite phase, so spontaneous emission cancels out. You can find the frequencies from this 2 by 2 matrix. It's kind of obvious. So this is your central complex frequency, and this is plus minus couplings as usual for Hermitian Hamiltonians. Now, what is very important for me, that your dimer state has this decay rate. It's real, it's imaginary part of this. If my two atoms are close to each other, this is small, because you get perfect destructive interference. If D is 0, you have infinite lifetime. As soon as D is slightly non-zero, you get lifetime, which is goes like d squared over lambda squared. So if your two atoms are exactly in one point, you get infinite lifetime. You start to move it, you get something. So people have actually seen this for two ions in a trap almost 30 years ago. So this is your dimer state at fill factor 1/2. This is a very important thing. Now, can you have subradiant state with fill factor 1? So what is state with fill factor 1 in this system for two atoms? It's a state where both of them would be excited, right? And it's not subradiant, because if they are both excited, they both can emit a photon. It's a symmetric decay, it's your superradiant state. So a lesson, incredibly far-going lesson from case of two atoms, you cannot have subradiant states with fill factor above 1/2 for n equal 2. But how general is this finding? So this we looked. So we calculated, we considered arrays of atoms up to 14, and you can have up to 14 excitation. And for each number of excitation, we have plotted the by color the smallest decay rate. So we find you have a lot of degrees of freedom. You have a lot of eigenstates. What is your darkest one? So, and what you see that here everything is bright, and here something is dark. So the finding is that you cannot have subradiant states in this model with fill factor above 1/2. And this is already not two atoms, so this is a big array. It's not so trivial finding. So as soon as your fill factor becomes more than 1/2, say you get more than 7 excitations per 14 atoms, okay, this becomes bright. So it's not a trivial finding. And then we looked, what is your...
It seems trivial.
Well,
If you have more excitations than atoms, then it's gonna go super radiant.
well, then
If
atoms...
you have only one more, it's gonna be super
No,
radiant.
then atoms for sure. Well, you cannot have more excitations than atoms, just there is no space.
Okay,
So
so
here,
but as soon as you have more than the 1/2, it's gonna go super radiant.
yeah, you are right. But well, it's not necessarily there are more degrees of freedom, but you need at least two atoms to cancel in destructive interference from at least of two atoms to cancel emission of one photon. We can prove it. It's not so easy a proof, but in a nutshell, yes.
Sorry, so we can go back there.
Yeah.
So if I understand what you mean by no subradiant states, because it seems to be a complete, like you draw these two lines, but it seems to be a continuous plot. You're switching from having less and less emission. So like which state is subradiant and which state is
Well, this can be rigorously answered in the limit when d goes to 0.
okay.
If d goes to 0, everything between below this line will go to 0 as d squared.
Okay.
And everything here will remain on the order of gamma 1d.
Okay.
Now, this was calculated, I don't remember for which d, but even like for 5%. So now this is my last like non-summary slide. So how does look your most excited subradiant states? So we learned that if you have small amount of excitations, your most subradiant states are some plane waves of polaritons. If you have a lot of above 1/2 fill factor, you don't have subradiant states. What is like last subradiant state standing? Yeah, but how will it look like in space? And for this, we have an answer. Yeah.
I have a question about the D, sorry. How do you define it for more than two atoms? Like,
D?
Was the.
It's a period, distance between two neighbors.
But it's so you're taking states where they're separated.
No, it's array, this is D. This is D. So how will this sync? How will your most subradiant state with fill factor 1/2 look like? And your general subradiant state is entangled, chaotic, and things like that. But your most subradiant state with fill factor 1/2 will be a product state of nearest neighbor dimers. So 1 and -2, 3 -4, and so on. Here I chose an even number of atoms.
Or you skip 2 minus 3.
Yeah, that well, no. Let's first agree that we have an even number of atoms. Then it's the only way to, like, you could not have two excitations on one array, on one atom. So I skip 2 minus 3, but you can ask another question, why it's not 1 minus 4, 2 minus 3. There are many ways to build such a dimers. Why you build a dimer with two atoms on with always neighboring atoms? Why dimers are so small? Why not? And for this, we have an answer from previous slide, because dimers, small dimers have longest lifetime. If you have a dimer with more spacing between atoms, you increase your lifetime as you decrease 1 over time is proportional to d squared over lambda squared gamma 1d. It's just this thing. So if you increase the distance between atoms, you get less destructive interference, so your spontaneous emission becomes faster. So nearest neighbor dimers have longest lifetime.
Probably because of some coupling, right? Coupling is strongest and they're close to each other.
Dissipative part of your coupling, yeah, for sure. Yeah, you can say like that. And it's of course a feature of 1D model. So your darkest state has only closest dimers, and it has dimers, well, I guess it's this argument that if you have a fill factor above 1/2, you even don't have subradiant states. So with this, I will conclude. We have generalized this for multi-level atoms. We have actually done a lot of studies on driven dissipative model, where you have external driving to the system and you measure something. So we don't just do eigenstates, but I think that for today I will stop, and I will just say that your weakly excited subradiant states are, your single excited subradiant states are these running or standing waves. If you have two or several excitations, these waves interact, they can lead to quantum chaos and they can lead to localization. And pay attention to states where one wave vector is large and one is small. And when you have a lot of excitations, you have these dimers. So thank you for your attention.
We have time for additional questions.
What will happen if you have instead of one waveguide, you have two waveguides and this coupling between them? So you still have the same analog with the subradiant states.
We search on that. I guess you will. I don't know, but this is an interesting proposal, because if you want to think in a more applied way, say build I don't know, quantum computer, whatever, then people were thinking of a photon being in the left or in the right waveguide as a photonic qubit. So this is your dual rail system. And then in principle, this could, well, you could design a gate from that. So it's people even do superconducting qubits which are coupled to two transmission lines at the same time. It's a group in Sweden, they call it giant atoms. So it's because it's like so giant that it can couple to two waveguides instead of one. So it's an interesting proposal. We did not do much of that yet, but I think
Maybe kind of a general question, especially about the first part. You're talking about open boundary conditions a lot. How much would the problem change if you just close the waveguide into a ring?
yeah, well, very short answer is Probably even nothing. So for this, definitely
Yeah.
nothing, because fermiionization was first considered just for a closed boundary system. For this, also nothing. We actually checked it. Well, yeah,
No,
we
it's still
actually
on that
checked it.
edge.
So
You have a ring.
no, that's the problem. So exactly. So this will not happen
Yes.
because this need a standing wave. If you have a, so this will survive, I think. This will not, because you don't have a standing wave, you need to pin it. This thing, you will have bound states, but not bound states localized on the boundary.
So why go to the open boundary problem, which is non-emission and more complicated?
Well, first, I guess it's interesting. Second, if I'm thinking of any practical realization, so it's, I would say it's even the motivation you could think on. But second, if these are superconducting qubits, how many you are going to have? So we collaborated with some experimental groups. Like I have experience of working with samples of 6, and then they actually have a waveguide. So it's there. It's not so hard. Well, I guess they could make it a ring, but yes,
Okay.
typically you have it. Yeah.
So, are there any further questions?
How does the radiance depend on the filling factor for, say, your multi-exciting states?
The more fill factor you get, the faster they emit until they stop being subradiant above 1/2. So it's gradually increases, and then it stops. Well, it becomes superradiant. Eventually at fill factor 1, if all atoms are excited, it's your superradiant state.
Okay, so let's end this video then.